Let us start chapter 4 module 5. So far we have seen many examples of connected and disconnected spaces. Most of the example of connected topological spaces comes using real line, and most of the examples of disconnected spaces comes from R with lower limit topology. Also, there are spaces which are disconnected, such as ordinal spaces, but we have not discussed so much with ordinal spaces. Next, in this module, we shall discuss about some groups of Euclidean spaces and their connectedness. In fact, we shall discuss about those matrix groups which are called basically matrix Lie groups. Basically, these are general linear groups over C. General linear group over C is the collection of all matrices of order n which have positive determinants. We shall examine in this module whether its subgroups are connected or disconnected. To view this, let us consider an example. GL1R and GL1C. So, GLNR means set of all non-singular matrix of order n over C, and GLNR means set of all non-singular matrix of order n with entries from R. Hence, GL1R means set of all non-negative real numbers, and GL1C means set of all non-zero complex numbers. Now we know that the space of all non-zero real numbers is disconnected because a subset of R is connected if and only if it is an interval, and we know that set of all non-zero complex number is connected as well as path connected. We shall see in the general case this also true. That means we shall see that GLNR for any n is disconnected and GLNC for any n is connected, in fact path connected. Let us go to slide presentation. So let us start with general linear group over R and C. The general linear group over the real numbers, which will be denoted by GLNR, is the group of all n by n non-singular matrix with real entries, and general linear group over complex numbers, which we will denote by GLNC, is the group of all n by n invertible matrix with complex numbers. We shall call any subgroup of GLNC as matrix group. Now we can consider a topology on the set MNC of set of all matrices with entries for complex numbers. There are two ways to define the topology. In fact, we can think MNC as subspace of Cn square. Hence, we can consider the subspace topology of Cn square or MNC. Also, this topology can be viewed in the following way. Let AM be a sequence of complex matrices in MNC. We say that Mn converges to a matrix A if each entry of AM converges as m tending to infinity to the corresponding entry of A. That is, if Aij converges to Aij for all index ij. That means a sequence of matrix converges to a matrix if all the corresponding elements converges to the matrix in question. Now let us define matrix Lie group. By matrix Lie group we shall mean any subgroup G of GLNC which will be closed in GLNC. That means we can say in this way, a matrix Lie group is a subgroup of G have the following property: if AM is any sequence of matrices in G and AM converges to some matrix A, then either A belongs to G or A is not invertible. That is, any sequence in G which converges, then either point of convergence is not invertible, and if this is invertible then it will belong to Z. Some examples of matrix Lie groups. The general linear groups over R or C are themselves matrix Lie groups. It is easy to show that GLNR is closed in C. So, it will be a matrix Lie groups. Another example of matrix Lie groups are SLNR and SLNC, where by SLNR or SLNC we mean all those elements of GLNR and GLNC whose determinants are 1. These are called special linear groups. It can be proved that both SLNR and SLNC are closed in GLNC. So, they are matrix Lie groups. Another kind of matrix Lie groups are ON and SON. That means orthogonal matrix of order n and special orthogonal matrix of order n. A matrix A is orthogonal if it preserves inner product. That is, inner product of AX AY is equal to inner product of XY for all x y belongs to R to the power n. Equivalently, A is orthogonal if its transpose is its inverse. That means a matrix with entries from R will be orthogonal matrix if A transpose is equal to identity matrix, and special orthogonal matrix will be all those orthogonal matrix whose determinant will be 1. Now, the set of all n by n real orthogonal matrix which will be denoted by On is a subgroup of GLNC, because product of any two orthogonal matrix is orthogonal and inverse of an orthogonal matrix is orthogonal. Now, it also proved that the limit of a sequence of orthogonal matrix is orthogonal. In fact, this holds because A transpose is identity matrix, and this is preserved under taking limits. That means, to prove that On is a closed subgroup of GLNC, let us take a sequence An of orthogonal matrices in On and let it converges to A. We have to prove that A is also orthogonal matrix. Now, consider A transpose n be the corresponding transpose of that sequence. Then the sequence A transpose n also converges to the matrix A transpose. Now, since all of the member of the sequence are orthogonal, we have that A transpose for any member of this sequence is identity, and therefore, if we take the product of the limit, then that is also identity. So, the limit is also orthogonal matrix, therefore, the limit is in On. The set of n by n orthogonal matrix with determinant 1 is the special orthogonal matrix group, will be denoted by SON. Clearly, this is a subgroup of On, and hence this is a subgroup of GLNC. Moreover, both orthogonality and the property of having determinant 1 are preserved under limits. So, again SON is a closed subgroup of GLNC, and hence SON is a matrix Lie group. Since elements of On already have determinant plus minus 1, SON is considered as half of On. Next, we shall discuss about unitary and special unitary groups, which we shall denote by UN and SUN. We know that a transformation in general called unitary if it preserves norm. Here we shall denote the group of all unitary matrices as Un and shall define a matrix A as unitary if it preserves inner product, namely if inner product of Ax Ay is equal to inner product of xy for all vectors xy belongs to C to the power n. Equivalently, a matrix A is unitary if A product its conjugate is equal to identity matrix. That is, if conjugate of A is its inverse. Now, since determinants of conjugate of A is equal to the conjugate of determinant of A, we can prove that if A is unitary, then determinant of A conjugate product A is equal to 1 for all unitary matrix A. This in particular shows that every unitary matrix is invertible. The same argument as for orthogonal group shows that the set of unitary matrices form a group. Now, the set of all n by n unitary matrices in the unitary group Un, and it is a subgroup of GLNC. Next, we can observe that the limit of unitary matrices is unitary. This holds because conjugations of matrices passes through limit. Therefore, Un, that is set of all n by n unitary matrices, is a matrix Lie group. Now, the set of unitary matrices with determinant 1 is the special unitary group SUN. It is easy to check that SUN is a matrix Lie group. Note that a unitary matrix can have determinant e to the power I theta for any theta, and so SUN is a smaller subset of UN than SON is of ON. Specifically, SON has same dimension as ON, where SUN has dimension 1 less than that of UN. Next, we shall prove a proposition about component of matrix Lie group. Let G be a matrix Lie group, then the component of G containing the identity is a subgroup of G. We already told that the topology we have considered here comes from the topology of Cn square, or we can think as the convergency. This theorem says that the component which contains identity, that is a subgroup of G. So, we have to prove that if A and B are in the component containing identity, then product of A and B is also in the component containing the identity. Now, since A and B are component, therefore, there exist continuous paths AT and BT, both of which starts at identity and ends at A and B respectively. Notice that here it is said that component of G. Now in Cn square we have that every component is path component. That is why we can take path AT and BT. Now since AT and BT starts at identity, therefore we have that A of 0 is equal to B of 0 is equal to identity, and since A and B are the endpoints of AT and BT, we have that A of 1 is equal to capital A and B of 1 is equal to capital B. Therefore, we have that AT gun BT is again a continuous function from the unit interval to the component, which starts at origin and ends at the matrix A B. Thus, the product of two elements of the component containing identity is again contained in the corresponding component. Now we have to prove that if A belongs to the component, then A inverse also belongs to the corresponding component. This holds as AT inverse is a continuous path starting at identity and ending at A inverse. Therefore, we have that both product of two members of this component is contained in this component, and also inverse of any member of this component is contained in this component. Therefore, we can say that any component containing identity is a subgroup of GLNC. So, we have discussed about various kinds of matrix Lie groups. In fact, we have started with GLNC, which is our basic matrix Lie groups, and any closed subgroup of GLNC is called matrix Lie groups. Next, we shall examine about connectivity or disconnectivity of GLNC. Let us pass to slide presentation. Next, we shall prove that first GLNR is disconnected. In fact, if we take set of all matrices A in GLNR whose determinants are less than 0 and take the set of all matrices in GLNR whose determinants are positive, then we get two different components of GLNR. That means we get two disjoint open sets of GLNR whose union is equal to GLNR. Therefore, GLNR is disconnected. In contrast, if we go to GLNC, then we shall see that GLNC is path connected. This is not disconnected. To prove that GLNC is path connected, let A and B be two matrices in GLNC. That is, determinants of A is not equal to 0 and determinants of B is also not equal to 0. We like to find a path from A to B which is contained in GLNC. Let us consider the collection of matrices 1 minus Z into A plus ZB, where Z belongs to C. Now we like to find our required path in this collection, but this collection of matrices form a plane which is parameterized by the complex coordinate Z, and this plane includes A at Z is equal to 0 and B at Z is equal to 1. Now, any element of our required path from A to B should not be contained in the collection 1 minus Z into A plus Z into B such that determinant of 1 minus Z into A plus Z into B is equal to 0. That means for our required path, no matrix in that required path will be 0 determinants. But 1 minus Z into A plus Z into B is an n by n complex matrix whose entries are linear in terms of Z. Its determinant is therefore a polynomial of degree at most n in Z, and therefore by fundamental theorem of algebra its determinant may have at most one roots, and at these points it is possible that 1 minus Z A plus Z B will be of 0 determinant. So, if we delete these points from the plane 1 minus Z A plus Z B such that Z belongs to C, then only finite number of plane points has been deleted from this plane, and so this plane remains path connected. Therefore, we can easily find a path from A to B lying in this plane. This shows that GLNC is path connected. We can also prove that groups UN, the set of all unitary matrices, and SUN, the set of all special unitary matrices, are connected for all n greater or equal to 1. In fact, we know that every unitary matrix has an orthonormal basis of eigenvectors with eigenvalues of the form e to the power I theta. It follows that every unitary matrix U can be written as U is equal to U1 product of matrix whose diagonals are e to the power I theta and all vanishes into U1 inverse, where U1 is unitary matrix and theta is a real number. Conversely, it can be checked that this type of matrix are unitary matrix. Now, if we define UT is equal to U1 into the matrix which has diagonal elements as e to the power I into 1 minus t theta, ultimately produced by U1 inverse, then UT is a path starts at U0 and ends at U1, and here U0 equal to U1 into e to the power I theta and ultimately produced by U1 inverse, and U1 is equal to identity matrix. So, we get a path from U to identity matrix. This shows that it is possible to find a path in the group UN. Similarly, we can find a path also in SUN. Therefore, we can prove that UN and SUN are path connected. To conclude this module, we mention that the main theme of this module is that GLNC is a path connected space and GLNR is a disconnected space. We have also seen that the space of all unitary matrices and special unitary matrices are path connected. With this, we end this module as well as this chapter.